Thank you, everybody, for coming and waking up at this ungodly hour on a Friday morning. I was sort of expecting the room to be empty, so thank you guys for coming and choosing to listen to us for an hour or so.
Yeah, I think the ideal DEF CON should be, be 3 weeks long and there'd be one talk at like 4 p.m.
Yeah. All right, well, my name is Joe Grand, and this is Zoz.
I'm Zoz Brooks, yep.
And we are going to talk about a project called the BSODomizer HD. This has been a very difficult project, and we're going to show you some pretty fun stuff with also some pretty disgusting videos. It's going to be great. So basically, this project came about. We'll talk about this. We were working on a project. Zoz writes a lot of software. I design a lot of hardware. And we thought it would be fun to sort of do something again together and come up with a new ridiculous project. So before we even start, while everyone's still paying attention, what we ended up doing, and you'll hear the whole process, but we started working with something called FPGAs, and we'll get into that. And this was like a really, really complicated thing, something we'd never done before. This project wouldn't have happened at all if it wasn't for some serious help from some friends of ours that really their name should also be on the title, of the presentation and stuff. So these guys, Chris Banson, Lead Bunny, who runs the Hardware Hacking Village, suffered through some extremely late nights this past week trying to help us get stuff working. Rivas and Parker just helped us with FPGA. So it really shows the power of kind of the community and people willing to help.
Longhorn Engineer actually gave us some software that enabled us to first convert an image to the memory initialization stuff that we needed to put in the FPGA. So even the very start of this project really wouldn't have happened without these guys helping us out.
Yeah, a lot of swearing on IRC. All right, so the original BSODomizer, for those of you who happened to sit in on the talk at DEF CON 16, was our original project together that was a hardware-based man-in-the-middle type of device that you would put in between a laptop or desktop and a monitor. And normally it would just pass the video through just fine. But you could remotely trigger it with a remote control or set some dip switches on the board to have it trigger at certain times and intercept the video, and throw up a preloaded fake blue screen of death.
And that was, at the time, it was when the Parallax propeller was brand new. So a lot of people know the propeller from a later DEF CON badge, but at that time, no one had really used it for much, and it just came out and was really exciting. Works a lot differently, if anyone here has played with it, to a normal microcontroller, and it was capable of going fast enough to generate a VGA signal. But fortunately for the BSODomizer, the original one, old Windows BSODs, of course, are just text only, and that's all the mode that the original BSODomizer had, was to be able to generate a 1024 by 768 image of only text.
And if you want to screw with people, everything's open source. The links are at the end of the presentation. You can still build your own and use it. And this was really a good learning exercise for us. We like to screw with people, but we also like learning things. So this was like an attempt for us to learn about the propeller and then really annoy people. So somehow I got roped into this. Zoz had this great idea. He's like the visionary. He said, we should do another DEF CON talk. Let's do the BSODomizer HD. Technology has increased. Let's do something different. Let's learn about FPGAs, which is something that really I wanted to learn about, but had kind of been putting it off for a long time because I knew it was going to be hard. And this was sort of the catalyst to do it. And it's like, all right, whatever we get done, we'll share it with the community, of course. And maybe whatever we come up with will be useful.
Yeah, there's a lot of exciting stuff once you move to an FPGA because you're creating hardware in hardware with software. It meant that we could do a lot of things with an updated BSODomizer that the first one couldn't do, because the first one just generates a text screen. With an FPGA, as well as injecting full screen graphics, we could also do some other interesting and exciting things, which we'll get to.
Yeah, and that's something that as soon as we decided to do this, the first thing we had to do was figure out if we could even generate video on the screen. So it was like, all right, let's try to figure out some things. Do a little bit of kind of pre-development work before we submitted the talk to DEF CON and for Black Hat Tools Arsenal and all this stuff. So we sat down and said, what can we do? Well, FPGAs can generate HDMI video, so let's try to do 1080p. That's more of like something people use now, HDMI instead of VGA. Though it's funny because when we had released the BSODomizer, we were trying to get it sold through like ThinkGeek and a lot of hardware places to distribute them to people, and everyone's like, no one uses VGA anymore. But people really still use VGA a lot. So, it's something like HDMI, even though, we're going to move to DisplayPort and other things, like, it will still be a valid option.
Well, it's funny, like, everyone's a hater, right? So when we said we were doing this to a few people and we're doing 1080p, they're all like, what? No 4K?
Yeah, I know.
We're like, well, I think people are going to keep using 1080p for a while. Just relax.
Okay, so some of the features we wanted, 1080p, we thought it would be cool to have user-loadable images from an SD card. So instead of just preloading something in advance, you'll see that we didn't get to all of this stuff. We set some pretty lofty goals. We wanted to do some animations because now if we're able to write directly to HDMI reading from memory, we can basically modify memory in real time and have a new image come up on the screen or have a slightly modified image come on the screen. So there's a lot of possibilities for the mischief side.
One thing we had really wanted to do in the original one is, because it had some switches to switch between Windows and Mac mode, and then Mac kernel panics changed to scrolling down the black thing, which there's no way we could do that with the original one, but with the one we have now, we have the capability to capture the screen, and you could edit it in memory and scroll down the gray overlay to say it's crashed, reboot.
Yeah, once we get the receive part working. So we figured, well, the other tool was very mischief focused, and yes, you could use it for pen tests. Some people use it like they walked into a building, put the BSODomizer in place, and then had it say like, surprise, we were here, or whatever. But we thought, okay, let's see if we can try to legitimize it even more, given how huge pen testing is now in red teams. Like, let's see if we can try to do capture. And this idea actually came after we had gotten some of the HDMI transmitting working. We're like, well, it doesn't seem like it would be that hard to receive a frame at the same time, unknown to the user, because we could split the signal off, which you'll see in some drawings, and capture the HDMI stream at the same time as it's going to the sink, to the monitor. So that's sort of a future thing. You'll see we kind of ran into some issues there, but the base functionality is there, and it's just a matter of kind of tweaking some of the code. The hardware support is there, which is pretty rad. And then, we were like, well, you can do some video display calibration and whatever. But really, I think the most important thing is having, another open source tool, something people can learn from and take our chunks of code. Like, we are totally FPGA noobs, and we hacked a bunch of stuff together, but we've written some solid modules that people can take and put into their own projects. And that's the beauty of FPGAs, which we'll get into. So HDMI is, of course, the video standard of choice, I guess. The issue here is that HDMI is very high speed, and we all take it for granted of you plug something in and it works, but the signals are very, very fast. They're differential signals, meaning you have a positive signal and an inverted negative signal that travel together, and the pixels, the bits are being sent at a very high speed. That's done for noise immunity and for other electrical issues. So you basically, the things we're concerned with for the BSODomizer are the 3 video lines, and a clock line. There are some other things with HDMI, some digital control lines that are used to communicate with the monitor and some other things. There was a DEF CON presentation last year or the year before on fuzzing devices that have HDMI, so fuzzing monitors through the digital control interface. We're just looking at video in this project, but that could be rolled into it if that's what somebody wanted.
But so if you do the math, you're pushing over around 120 million pixels a second at 60 hertz. So that's just a lot of pixels. And if you look at the actual bit rate, it's 3.6 gigahertz. So there's just no way that you're going to find a microcontroller out there to do that.
Yeah, and FPGAs, as we'll talk about, are designed to sort of do heavy lifting of digital functions. So if you wanted to have, you could take differential signaling in and process it, but you'd need a really, really high-speed, powerful device. So we, decided we had to figure out a way to be able to process video and generate it in some sort of timely manner in real time. And dealing with the straight serial data is hard. So we ended up focusing on a system that we can now get a pixel clock of 148.5 megahertz, and that's going to simplify things a little bit by looking at parallel data.
I should read the slide instead of doing rough calculations in my head. So nearly 150 million pixels, not 120.
Yeah, close enough. That's all right. It's early. All right, so FPGAs, this is just a little bit of an intro slide. You'll sort of see our suffering through this, but FPGAs are field programmable gate arrays, and it's an electronic device that basically is like a blank slate of digital logic. So, microcontroller systems, computers, all the digital things we use are based on low-level logic, digital logic that's basically processing ones and zeros and doing stuff. So CPUs are built up of millions of gates or logic. FPGAs let you be the artist and sort of fill this canvas with whatever you want. As opposed to a microcontroller, that's running things step by step. You have your program counter doing things sequentially. FPGAs can do things in parallel, and you're not writing software, you're writing hardware, which was a great combination for us to sort of merge the two. And it's sort of like, and stuff is executing in parallel, synchronized to a clock or to different clock signals. And it's a complete mind fuck if you come from the software side or embedded system side of how a system's working.
For example, if you're a software person and you're used to putting a value in a variable and then using that variable and reading it back and having the new value be in that variable, then you'll be surprised with FPGAs because everything happens on clock ticks. So within a block of logic, if you set, for example, a value in a variable, it doesn't actually take that value until the next clock tick. So if you refer to that same variable in the same block of logic, it's still got the old value. So there's just like a lot of ways for a software person that's used to a normal programming language to fuck it up.
Yeah, and one of the things, I tried to explain this to my kids, because Zoz had come over a few times to work on this project, and we were slaving away for hours, up until 2 and 3 in the morning. So my son comes in one day and says, "Daddy, what are you working on?" So I tried to explain it, and I said, well, we're trying out a new piece of hardware called an FPGA. It's much different than what Daddy normally works with, which are microcontrollers. I said, microcontrollers, you can, pat your head first, rub your tummy second. FPGAs, you have to do both at the same time. And he tries it. He's like, "Oh, that's hard." I'm like, "Yeah, that's why we're staying up so late." So FPGAs really traditionally have been very, very, very complex systems. The development tools have not been free. They are definitely not user-friendly, but they're becoming more accessible. And this is something like you can look at projects now, and you might see an FPGA on there to do, say, some hardware acceleration or some crypto or video generation. And then usually there'll be a microcontroller associated with that to do the normal microcontroller stuff that doesn't have to be in an FPGA.
So there's two hardware design languages that you can, or hardware description languages that you can choose to use. One is VHDL. For anyone who's done any programming for the DoD, it's a lot like Ada. It's got some sort of strong typing. It'll stop you from shooting yourself in the foot in certain ways. And then the other one is Verilog, which is sort of more C-like, and just like C, it'll let you make all kinds of mistakes and not warn you.
It's horrible.
So partly because we've done a lot more C recently. My first programming language was Ada, but I haven't programmed it in a long time. And also because of the tools that were available for the FPGA we were using, we used Verilog. And it really, there's just lots of things that it won't warn you about. You can refer to signals that don't exist and do all this kind of stuff. You can put a typo in. What was the one where you were using a different clock and it was just like a typoed clock?
Yeah, I made up a clock name because I typed it wrong and the system didn't tell me. So probably 4 or 6 hours of trying to figure out what it was the wrong name. And to make matters worse, with development systems, as the complexity of the logic you're trying to compile and synthesize grows, the time it takes to compile and synthesize grows. So when we were working on the project, it basically took between 10 and 15 minutes per compile to synthesize our code, put it into the FPGA, and then execute it. So you can imagine the boredom of sitting there while it's compiling, and we would end up, so you make a change, you compile it, it runs, it doesn't work. Now you make another change, you do it again. So we would try to fix our problems that we found while it was compiling and do it again. But it led to the thing of like, which problem are we fixing and what new things are we introducing that are going to cause another problem?
Yeah, and if you have to express, like if you're used to just tweaking a tiny thing and quickly testing it out and iterating fast, you just can't do that when you have a 15-minute compile time. It's like you try 4 different things and there's an hour gone.
So one other thing with FPGAs I want to mention is there's something called IP, or intellectual property, that are basically logic modules that you can buy or license from other companies. So for example, if we wanted to, like with our development board that we have, Altera makes something called the Nios processor, which is a CPU, some architecture, I don't remember what because we didn't use it, but you can license that from Altera. So now you can have a microcontroller inside of your FPGA to do microcontroller stuff, and you write code in C. So if you're reverse engineering a piece of hardware, for example, and you find an FPGA in there, you're not going to know what it does because it's literally a blank slate. The problem, though, is that we didn't want to design anything that required licensing IP because that's totally lame. We wanted to do something where all the logic defined what it was and not rely on that. So a lot of the example code that came with the development board was all based on this Nios CPU that we didn't want to pay licensing fees to. So we had to create, our own lower level interfacing. But the beauty of the FPGAs is that you could go out to like a place like opencores.org and choose things that are open and free and integrate those into your products and basically make your own custom chip.
We also felt it would have been kind of cheating for us to just drop a microcontroller in the FPGA instead of doing everything by hand.
Yeah.
But
so,
we should move a little faster here because.
Well, I guess the takeaway here is that FPGAs are really hard. Okay, so the process is, first thing we like to do anyway is put together a block diagram. This is an early one that doesn't hold true too much, and I'll show you a better kind of connectivity graph of how things go together later on. But the two main things we needed to work with at first when we started the project was find an FPGA that had some sample code that was accessible, that was available. Zoz came over to my house for a week, and we basically had 4 days of time to source the starter kit, to figure out what FPGAs are, what we want to do, and then get the thing in hand and see if we could generate some video.
Yeah, at this point we hadn't decided to submit to anything, so it was like, okay, we got 1 week, let's get a dev board, get it up and running, prove that we can do the thing that we are going to say we're going to do, the main thing, the injection, and then we can know that we can get it done. So
this board has a lot of functionality on it. It's a very powerful part, so we don't actually need all that power, but it's better to start large and sort of cut back. But it had, some dip switches and things that we can use for our triggering, a lot of GPIO that's going to be useful for the HDMI receive. It also had what's called an HDMI transceiver or transmitter. And what it does is take parallel data that the FPGA gives it at the pixel clock of 148.5 megahertz, serializes it into the high-speed HDMI format, and pipes that out. So now we don't need to generate 3.6 gigahertz bit rate signals, which you could do with some FPGAs, but they're going to cost you a lot of money. So using this one, now we have this chip that takes the FPGA data that we're generating, passes it through, feeds it out to HDMI, which now it sounds like, oh, it's easy. All we did was pipe some parallel data through, but that's not actually true. We thought it was going to be very easy. It definitely made it easier. So here's what the early proof of concept looked like. It was the development board hooked up to HDMI. You can see like some extra hardware along the side. I'll talk about that. But it was some unique kind of power things we had to deal with. So yeah, we talked about that, FPGA development being slow, tools are hard, but the goal was to figure out how to draw something on the screen.
So the sort of main thing that we had to do here is the block memory inside the FPGA that we had is only, I think, 512K. So not big enough to hold a full frame buffer of a color 1080p image. So what we did instead was put in a monochrome image because there's only 2 colors on a blue screen of death. So as long as we can display a BSOD, no problem. So we loaded a monochrome image and then just set, instead of black, to the Microsoft blue that the slide's background is. And to do that, we had to start with a source image and convert that to what's called a memory initialization file, which is this thing that the FPGA takes that just fills up that block RAM. So you have to put it in the format that it needs with the right headers and the right size for the block RAM. And that's where Longhorn Engineer really helped us out that week, because he had this image to MIF function that he'd sort of half written. It took in certain kinds of images and certain kinds of bit depths, and he gave us that, and then we forked that and made it do the things that we need to do to generate the 1080p, or to load the 1080p monochrome image.
Which his was designed for a Game Boy. He had hacked a Game Boy to take the parallel data that was going to the LCD and then port that to a larger screen. So he was only looking at 4 colors. So yeah, Zoz had modified the code to basically take in a bitmap and then pack it into a 1 bit per pixel 1080p, because that's, like he said, the only amount of space we had in the internal RAM. And putting things in internal RAM is good, but it's sort of a pain because you have to preload as you compile the FPGA. So that's one example and one function that we have in the tool, but not the ultimate one that we wanted. But that was the one that we first could use to prove the concept.
Yeah, the problem with doing that, we want the thing to have a bunch of different modes where you can output different images, and so using just the internal RAM, that gets loaded at the time that the FPGA is compiled, and so it would you'd be limited to just that one image if you did it that way.
Which is okay, because that's what you get for now, because that's as far as our code gets. But the functionality, the hardware is there to do more, which we'll talk about. So the other issue is we got the FPGA board working. We could display some video, and we'll go through some of the pictures. But one issue we had is, how do we power the thing? Because if this ends up being an actual tool that you're going to inject in somebody's place or facility, you don't want to have to plug in a power jack to it, right? Or a wall wart, or plug in like a USB cable to get power, because that's just lame.
So the original BSODomizer had you can see the clip here for two CR2032 batteries, the same ones that are on the DEF CON badge this year. And that's because you don't get any power from VGA. This time, we were really excited, right? Because we're like, yeah, you get 5 volts from the HDMI. It's going to be super simple. It'll power itself off at the HDMI line. And then we looked up the spec, and you can only get 55 to 100 milliamps of power off that 5-volt line. And we're just, fuck, right? Yeah. Shit.
Which is not enough.
We're thwarted here. And we looked around, and like, there's a lot of devices that violate the spec. There's like sketchy Chinese HDMI devices that just they don't care. And so a lot of HDMI suppliers, like devices will sort of let you violate the spec, but we wanted to do it right and make a device that followed the spec, especially because if you're going to use this for penetration testing, you don't want to plug it into some machine and have it cause problems and have someone notice it right away.
Yeah, you don't want to interfere with the target, right? So we had to figure out a way to get that working, and it turns out, as you'll see the block diagram, we ended up designing a front-end board that handles a lot of the timing, the remote triggering and stuff like that. And we have a circuit on there that basically will allow normal pass-through mode of the HDMI signal and charge a battery, trickle charge a battery, while the system is technically off. So while we're just doing pass-through. And then when the user will trigger the BSODomizer, that enables the rechargeable battery, and the battery itself powers the FPGA board and just turns it on when it needs through a single line to a MOSFET, which is kind of cool. So we'll get into some details of that, but that was a way to overcome the power sourcing issue, is have a battery and just have it trickle charge, and it will last many hours, as you'll see. So yeah, the 1080p 1 bit per pixel, our first test. This took a few days of time to get going.
Actually, my flight back got canceled due to storms in Houston. I had an extra day on the week, and that's when we got it working. We didn't quite make the original week, but I had that extra day, and then we got it working. And it was just like, it just was like being back in the 80s and driving a CRT screen, where you'd compile everything, 15 minutes, you'd hit the button, and then the vertical hold would be off, and the image would be scrolling crazily, or it would be smeared across the screen, and you just be like, what the hell is going on here?
Yeah, because we needed to, just like I'd written an Atari 2600 game 10 years ago, I guess now, just for fun, and you have to deal with like tracking the scan line before you draw your graphics. It's the same thing. We need to know where the scan line is, really, what pixel we're on, so we don't end up having timing issues. And this is really when we started, once we got video on the screen, or an image on the screen, we're like, yeah. But then once we started debugging it, we're like, fuck. Like, that's when we realized how hard it is to work with FPGAs. The debugging tools also, by the way, are very, very limited. There's something called a signal tap, which, at least with Altera, is a logic analyzer that you can compile into your code. So you're basically looking at gates and at nodes inside your chip. But every time you add a new node and you're like, oh, I want to look at this line, you have to recompile it. So it's very, very hard. And we ended up using it. It did save our ass at the end, but it was a hard process to get through, like, why is the pixel shifted and everything. So these are sort of the...
So one problem, there's lots of things you can clock off on the FPGA. Yeah, that's me, looking for glitches with a magnifying glass to see if we're really, that line of pixels is properly vertical. But you can clock off a lot of things on the FPGA, and one problem we had was figuring out what line we were on, and we were clocking off the pixel clock, and we were like, why aren't things on the right line of the display? And it turned out it's because the pixel clock keeps counting during the horizontal blanking time. There's no real reason you have to do that, digitally, but it's just like old school, like how you would redraw parts of your frame in the horizontal blanking time to counteract the fact you didn't have enough memory back in the Atari days.
And do processing in the time where it's not drawing on the screen. So there's still some function for that, and I think it's sort of a holdover from CRTs. But once we solved that problem, now we could actually display something that we had preloaded into the internal RAM, which was killer. So here's our first little BSOD that came up. I don't remember which version this was. Windows XP?
Yeah, maybe. I'm not sure. This might be actually... a BSOD from the original BSODomizer development. I'm not sure.
That we grabbed. This is yeah. Oh, so I don't know whatever year that was.
Yeah.
So what we did then is, all right, we had this is where it gets really bad. We had the proof of concept working. Zoz was about to leave, and we're like, well, we need some video to submit to DEF CON to show that we can at least generate video, and then we'll worry about everything else later. Like, once we can do HDMI, the rest of it's going to be easy, which was so not the case. And I think we sort of got suckered because even though it was hard, we got it. And we're like, yeah, this is FPGA is nothing, piece of cake. So we needed to make a video, and my wife happened to be around, who's not very technical. Though some of you guys might remember her from calling me when I was on stage talking about the DEF CON badge from a long time ago, and she was pregnant with our first child, and I had my phone on, and she calls, and there's like 3,000 people in the room and stuff. So she's been here a few times, but she's not technical. We're like, can you just like pretend to be using your computer, and I will manually BSOD you, and then like you'll see a blue screen of death.
And this was, because you probably have seen the announcement that the new Win 10 BSODs are going to have a QR code on them. So it was like, this is perfect. We'll generate like one of these newfangled BSOD screens with the QR code and get her to scan it with the phone. Then we can,
which she'd never done before.
Yeah, and then we can use that QR code to send her somewhere that she won't expect.
So we basically told her, like, use this app, scan the QR code, pretend, just act it out. But you can see the point in time where it goes from like very obvious acting to very obvious like WTF is going on. So here's the first of 3 videos that we have that we'll show you throughout the presentation.
What? Frowny things? What the fuck just happened? Oh, critical process died. What does that mean? QR code. Let's see. Help me?
You've just been BSODomized and rickrolled.
So she basically was like, what the hell is this? This is the dumbest thing ever. If you guys actually focused your time on like doing something useful, imagine what you could do. So then, yeah. So she had no idea about QR codes and the fact that you could preload it with a malicious URL. So imagine if you're actually using this for a pen test and have somebody scan a QR code and then go to a malicious website, pwn their phone, whatever it is. But the Rickroll is classic as she had no idea what it was. Okay, so we had that working. We submitted the talk to DEF CON. Now we said, now we need to actually try to get done other functionality. And that consisted of making sure we could power it, making sure we had a way to control it instead of using dip switches. We didn't have enough space in block RAM for the full 1080p 24 bits per pixel, so we needed a way to use external DDR2 RAM, low-power DDR2 SD RAM, which is on the development board. And we figured dealing with the block RAM was easy, so how much harder could it be to deal with external memory? And we were way wrong about that. We also wanted to have an SD card, so you could preload images and, with the screen capture mode, save those images back. And as you'll see, the hardware's in place again, the code, not quite, but all of the heavy lifting, kind of low-level memory reading and writing and displaying is done, which I'm really, really happy about. So the rest of it, which is funny, I say this every time, shouldn't be that hard, but we'll see, we'll see if that happens. And we needed to combine it into something that was useful.
So the main thing is, as we mentioned with the power consumption, the FPGA is the thing that draws all the power. So we want that to be basically off as much as possible while the battery is trickle charging. So to do the front end's got to be, because we wanted to drive it with trigger it with an infrared remote control, something's got to be awake all the time watching for the infrared signal. So we decided to use a PIC for that because Joe had a board he was working on shortly prior to that was all already set up with broken out for development. So we just used that board to make our lives easy and save time with the IR external trigger, the part numbers there, and also the timer mode. So the front end PIC keeps track of time for timed mode. So for when it's just goes after 10 minutes or so, and it also monitors the battery level. Yeah.
So what we can do is you can trigger the BSOD, but then have it not actually go off for 10 minutes or 30 minutes or something, so you walk away and do it. And really with the front end, what we have is just that single line to enable the FPGA. So if you wanted to modify this and say, well, I want to use Wi-Fi or I want to use Bluetooth to remotely control stuff, you can, and just feed in a different output to that FPGA and move the PIC. But this is all low current stuff that's running all the time.
The original one, we just used Sony TV codes because everyone's got a TV remote control. But for this one, we thought, well, this was Joe's idea. People, if you're walking around a facility with a big fat TV remote control, in the office, people are going to be like, "What's going on here?" So it would be cool if it used a more covert remote. And now you can get a lot of these little Apple remotes surplus from various surplus places. So Joe was like, "All right, I'm going to order a bunch of Apple remotes and let's figure out how hard it's going to be to trigger off this instead of using a standard TV remote."
Yeah, and a lot of the information online that we found about the infrared remote for Apple, people have reverse engineered them, but not a lot of the information from the different websites lined up. Some pieces did, and we ultimately just created our own kind of brute force decoding mechanism and then just identified where the signal was sending the command signal for the 6 different buttons that we were using.
Yeah, you can see on that oscilloscope trace there basically how the format works. It's a transmission protocol called NEC, which is not the version not the protocol that we thought it was going to be initially. But there's this one sort of long pulse to begin with, and then there's a short space after that, and then it clocks the bits in, and it's just the width of the pulses is the width of the bits. So looking for that sort of start pulse and space gets us started, and then all these bits came in, and we couldn't. A lot of what those bits are, we don't know what they are. The stuff online is contradictory and confusing, but we figured out the space that uniquely defines which of the 6 buttons is being pressed, and we just read those out. Once we figured out that the bits are in the reverse order, which also wasn't documented anywhere.
Yeah. So I should mention too that the front end, the microchip PIC stuff, is standard microcontroller written in C. So you could take this code, that we've done for Apple decoding. If that's all you want to take out of this presentation, take it and plop it in something else to now decode Apple Remote. So there is some stuff in C that's a little easier to work with. For the HDMI receiving, we're using a ADV 7611, so basically the opposite of what we're doing for transmit. We're transmitting, we're pushing in parallel data, getting serial out. This, we're receiving the serial data from a chip, and then the parallel data goes into the FPGA that can then be clocked in and ultimately stored into memory, which can then be used. There's a board called the HDMI Lite, which is a project that somebody put together that takes HDMI in and kind of just very simply reads some of the color pixels around the edges of the screen and then turns on some RGB LEDs around his bezel of the screen to sort of extend the color, which I think a lot of TVs are doing now. So we use that as a breakout board, sort of a reference board, since we didn't have time to make our own board to get stuff done. So we use that one and then hook that up through an interface board to the FPGA. So we have this stack up that you'll see. It's pretty wild. And for this, we had use my PC board prototyping machine, which generally is good for creating lots of interface boards. And we ended up with this was a standard board, just taking one set of pinouts and converting it to another. But the trick is that we had to deal with 12 mil traces, 12 thousandths of an inch, which are pretty small. Not so small like when you're getting a PC board professionally fabricated, that's not a big deal. But when you're milling stuff, because this basically is milling traces out of copper, there's a lot of mechanical stress, and those traces end up being very small. And what ended up happening is, as I was soldering the connectors on, the glue between the copper and the fiberglass of the circuit board was getting delaminated because those traces were so small. There was no solder mask to protect the traces and stuff. So I ended up having to go in and manually repair stuff on a 0.1 inch header, double row header. It was a nightmare. But now it works, and we have hardware interfacing. So that was just another part of the stack up of circuitry.
Yeah, and that took the smallest milling bit that the T-Tech takes, and we broke a milling bit. Then we had to hand fix everything. So it's just another step where it's like, oh, here's an easy thing. Let's just spin out the circuit board, and then next thing it's 2 a.m. and we're all swearing.
But without that would have been an issue because we couldn't hand wire that board because the speeds of the signals, like 148 megahertz, seem slow, but it's still pretty fast. And if we were hand wiring things, if the lengths of the traces were longer, some of them were longer, some of them were shorter, that could introduce some timing errors. If there was any sort of noise that was picked up by longer traces, so we needed to have some sort of carrier board. We had some other subsystems in there that I'll show you in some pictures, but really I wanted to show you the actual prototype that is also on the stage, and that was used to create the next set of videos that you'll see, is what I call the circuit board sandwich.
Yeah, wrong sandwich picture, Joe.
Oh, sorry, okay, this one. There's the real circuit board sandwich. So this board is the stack up. Down at the bottom, we have the FPGA board. Up there is the HDMI light board that we're using for the carrier. There's also the interface board that you can barely see. You guys are welcome to come up and take a look at this after. There's the PIC front end board, that whole board up there that has the infrared remote, the battery charger. There's the battery charger. There's the HDMI splitter. So when we're doing HDMI receive, we need to actively split the signal, because if you're tapping into high-speed signals, you could introduce noise and glitches and other things just passively. So having an active splitter means you can pass the HDMI signal to the target monitor. The user would never know, and then you're sucking off the HDMI to do your capture on. So that's what that board's for. And then there's the HDMI switch, which is switching between the target system and our generated HDMI signal. So I'll leave these in here for you to review later. Just some drawings of how to understand how the system goes together. And these were really helpful for us to graph and sort of put down on paper what was happening. It was a very confusing process. So current measurements, yeah, we basically, with our battery, it's about, it's a lithium ion, it's about 1.5 inches or maybe 2 inches by 2 inches, 2,000 milliamp hour. You can run for about 3 hours of active generating HDMI. That's never going to be the case, right? Because you're going to throw up a BSOD, and a minute later or less, somebody's going to turn off their computer, the system's going to reset, and then it will go back to pass-through mode. So you can get a lot of battery power, and then, of course, it's going to charge while it's not being used, which is most of the time. The main challenge we had was dealing with the external memory and getting external DDR2 working, where now we're dealing with 24 bits per pixel, 32-bit words. To simplify 3 weeks of complete pain and tears and suffering and everything, what we ended up having to do is double the speed of the clock signal going to the external memory, and we're basically clocking things twice as fast to the memory as we are to the screen. So we can read data faster from memory, put it into a FIFO buffer, and then as the HDMI transmitter is ready for it, it can grab it from the buffer. So we're sort of preloading a cache, I guess, if you will. And this was something that Lead Bunny had helped out with, some serious stuff. We had to implement a burst mode of the DDR2, which basically we were reading 128 bits at a time. We tried to do pipelining, and it was like this. It was the worst experience of my life. But now that it works, it's awesome, and we learned a lot about the development tools and stuff. But here's sort of some videos. You saw some pictures, but this is basically like a week before DEF CON. And we keep seeing like, oh my God, we're close. We can kind of see things.
Yeah,
but
so
it's
this is after a successful write to memory. That was working
Yes.
just fine. But then reading it back in, we get video after video after video like this.
And writing it is actually easier because we don't have a time constraint of trying to draw to the screen. But what we needed to do here is drawing to the screen by reading the memory and then writing it in real time. So eventually we got stuff working, and this was sort of Zoz in the midst of some of our debugging early on. And yeah, so we basically are like, FPGAs are really hard, they suck, but there are actually good practical uses for them, right? So there are uses for them, and it's just picking out the useful things, especially things that can't be done in sequence. So I just wanted to throw this picture up. You can't really see it, but you can generate what's called an RTL, which is basically a schematic representation of our logic design, and each of those blocks are a separate set of code, creating this massive digital custom system of our own. All right, so now the part you guys have been waiting for. This was something where I had, so Zoz was away, and I wanted to have some more videos of real BSODomy, right? Once we got the remote triggering working, all the front end stuff. So some guys came over, you might recognize them. One of them is Anch, who runs the registration, and one of them is Crypt, who helps run a lot of DEF CON now. They came over, I created a special image for them, and I'll just show you the video. So to lead up to it, my kids were there. They love these guys, and I told them, I said, convince them to watch something on my TV screen. So they basically convinced these guys to watch like a Pokemon. Basically, my wife dressed up as Pokemon, and the kids chasing her down the street in our neighborhood, because we didn't want them to play Pokemon Go, because we're paranoid about privacy, of course, as we should be. So we decided to do Pokemon Go in real life. So they were trying to, my kids convinced these guys to watch this video, and then you'll see what happens.
Yeah, and I actually have not seen this video yet.
Yeah.
Joe refused to show it to me until the presentation, so I'll be joining you guys in watching it for the first time.
Also, if there are any young children in the audience, cover your ears. If you're with your parents, make sure they cover your eyes. There's some nasty images on the screen. As a fair warning. Okay, here we go. He's watching the video.
This is horrible technology.
What just happened?
I don't know. Goats.
That's what you did. Well played, sir. Well played.
Thank you. That's why no children are allowed in this office. Or I like BSODomize you in 1080p.
I'm correct, bitch. That's pretty good.
I'm just not into it.
It's his favorite. It's his favorite.
So, here, I'll put it back now.
That was well played. Did you do it remotely? Or was that time?
It's remotely.
That's nice.
With the Apple remote.
Sony remote this time?
No.
Same.
It's a little more sleek for the office space.
Exactly. I love it.
And now we're back. No more goatsy. Sorry I had to do that to you. BSODomy in HD, successful.
I approve.
Yeah, so... Okay. So Ansh was basically disgusted and was texting his wife. Joe Grand just goatsied me. But what happened is they were so loud that my kids who were outside playing, because I told them I was like, I'm going to show Jeremy a really disgusting video, like you can't come in. So they heard all the noise and decided to come in. So I'm like, all right, I'm going to BSOD them too. Children are not immune. But no, not with what you think. All right, so now, now the kids are watching the video because they think it's funny.
What happened?
Daddy.
Did you break it?
No, Daddy uses BSODomizer.
You guys have trained well. Yeah, so Daddy's using his BSODomizer. Watch out. So you could see on the screen there was some static on there. That's another mode that we generated to show that we could do animated video generation, is now you have static, which is awesome for kids because if you hook this thing up and they're watching TV and you don't want to be the bad parent by saying you got to stop watching TV, you just, turn on the static mode and be like, oh, I guess the TV broke. Got to go play outside. So we had some other modes in there, mostly used for testing, some moire patterns, some grayscale stuff, and that's all still in there, so if you need to have like a legitimate reason to build the tool, you could do that. But really it comes down to the challenges of dealing with the FPGA, designing the system in essentially 5 weeks of full-time work with us across the country, and Zoz basically receiving a bunch of emails of me bitching about stuff and like once in a while sending a picture. I did send him the goatsy of the image on the screen. I didn't hear from him for a few days. I'm like, oh shit. I know he's hard to piss off, but I wonder if I really pissed him off.
No, I just wasn't reading email for a few days due to travel.
So the challenges of this is we picked something way outside of our comfort zone, and I'm proud that we were able to get to a point where we have stuff to share, we have stuff to show. There's other FPGA nightmare stories, and anybody that's worked with FPGAs is probably like, haha, you guys suckers. But things about even like dealing with the different signals at different clock speeds are like a really hard thing because you have to synchronize stuff, and that's what we did with the buffer, or you're going to have all sorts of problems. Things like we need to generate a new clock with a phase lock loop, a PLL that's in hardware, and the SDRAM interface, the DDR2 RAM interface, was using the PLL that we were trying to use, and it took about 4 hours to realize that we were not using the right one, and we had to physically specify in code where we wanted to physically place a piece of hardware inside the silicon, which was pretty mind-boggling. It was a lot of fun, kind of a hard project. If you want to start working on your own project, all the code for the old design is up on my website. The development notes and the schematic for this project will be up once I get back to a safe internet connection and I can scan all my documents in. There's 2 GitHub repos, one for the C code for the front end, one for the HDL for the FPGA. So everything's available that we've done will be online. The main thing I think here is that FPGAs do fill a gap, like they're useful for certain situations if you know what they are. Definitely don't be scared to start using them and get involved. Like there are some simpler FPGA boards because being a hacker is all about expanding your knowledge, right? And trying something new and learning from it. And like even if this is a completely ridiculous project, I'm confident now that as an engineer I can go and like design something with an FPGA.
Yeah, we definitely don't want to scare people off, with saying how hard everything is. Just that there's a learning curve, like there is to anything, and you have to not be scared of it and to dive in and just commit to a few weeks of frustration to getting everything up and running. But once you do, you'll be like, wow, this is a really cool, powerful new tool in my arsenal.
That's right. Yeah, so the final question that people have been asking us a lot is are you going to turn this circuit board sandwich into an actual product? I don't know. There's a lot of engineering that still has to happen, mostly from the hardware design side. Zoz is sort of like the...
Yeah, I really want to do it, and Joe's not sure if he wants to do it. It's a classic kind of Jobs-Wozniak situation going on here, because it's really easy for me to say, yeah, we should get this in people's hands. People will really love it, they'll use it, but Joe's the one that has to do all the hardware design.
I'm going to be stuck with it. So, yeah, depending on if people want it, whatever, we set up an email address. You could send comments and suggestions, but everything's up there, so you can at least start hacking on stuff on your own. So,
but yeah, if you want it, if you would buy one, send email to root@BSODomizer.com, and then we'll gauge demand, and then maybe we'll make it.
So, yes, thank you for coming, and the end.